Intro to Inorganic Chemical Nomenclature, Part 1, Binary Compounds. This lesson was divided into two parts owing to its length. Part 1, Binary Compounds. In this first video, we are studying the nomenclature of binary compounds. Now, there is also a second video dealing with the nomenclature of polyatomic compounds. And if you wish to search for that, it's on YouTube under the name Inorganic Chemical Nomenclature, Part 2, Polyatomic Compounds. Now, chemical nomenclature means writing the formulas and the names of chemicals. We're going to be using three systems of inorganic nomenclature: the stock system, the prefix system, and the us-ic system. Now, this will require that you learn the names, the formulas, and the oxidation numbers of a variety of monatomic elements and polyatomic ions needed for binary and polyatomic compounds. This lesson is designed for a first semester college chemistry student and assumes that the student already has a working knowledge of electron configuration, electronegativity, chemical bonding, and acid ionization. Now, I'll be making reference to these concepts and briefly reviewing them throughout the lesson. Let's begin with chemical formulas of binary compounds. Now, a binary compound is one that's made of two different kinds of atoms. That's what the word binary implies, two. A chemical formula will tell us which atoms and how many atoms of each kind are present in a chemical compound. We'll start with a familiar example. Look at the structure of a water molecule. We can see that each water molecule contains two hydrogen atoms and one oxygen atom. So how would we write the formula for this molecule? Well, H2O, we see that the symbol for the element hydrogen is shown, H. The symbol for the element oxygen is shown, O. And we have the subscript 2 following the H, indicating that there are two hydrogen atoms in each molecule. But we do not see a subscript of 1 following the oxygen. It is implied or understood in the formula. So, first rule is a subscript of 1 is never written in formulas. Look at the formulas on the right, and let's identify the errors in each case. Here I have the formula H2O1. What's wrong with that? Well, we just stated that 1 is not written in a formula. How about H2O? Well, in this case, the 2 is in the wrong place. It should be subscripted, not superscripted. How about this H2O? I have hydrogen in parentheses. Well, when you only have a single type of atom present, and there's more than one of them, we don't use parentheses. We'll see later that when you have groups of atoms called polyatomic ions, and there are multiples of them, then those groups are placed in parentheses, but not for single atoms in. And how about this last example? What's wrong with OH2? Well, I think we know from experience that it should be H2O. The reason that it's H2O and not OH2 will be explained on the next slide. So here I have the electronegativity values of the A group elements. These electronegativity values are the numbers written in parentheses immediately following the atomic symbols. And before we begin, let's do a quick review of this periodic table. Elements which are metallic are colored green on this table, and they are to the left of what is called the staircase, this dark line that looks like a staircase, except hydrogen, which is a nonmetal. Nonmetals, colored orange on this periodic table, lie to the right of the staircase, and they include hydrogen, which is truly a nonmetal. And then the elements that touch two sides of the staircase and are colored yellow are called semimetals or metalloids, with the exception of aluminum, which is truly metallic. So, in the case of water, H2O, we need to get the electronegativity values of the elements to know how to list the order in which to list the symbols. Hydrogen has an electronegativity of 2.1 and oxygen is 3.5. And since hydrogen has a lower electronegativity than oxygen, its symbol is listed first in the formula, H before O, and that's our next rule. The less electronegative atom is listed first in a chemical formula. So let's do some practice. How about you write the formula of a compound made of 1 sulfur and 2 sodium atoms. Well, you'll need to get the electronegativities of each atom. Sulfur is 2.5 and sodium is 1.0. Since sodium is less electronegative, it would be listed first, and there are 2 of them, so we'd write Na2S. Now, since you've already taken some chemistry, you will recognize Na2S, sodium sulfide, as being an ionic compound made of a metal ion, sodium, and a nonmetal ion, sulfide. And it's true in every case that all metals have lower electronegativities than any nonmetal. So you don't actually have to look up the electronegativity values of ionic compounds. You simply have to recognize that the metal is always listed before the nonmetal. Now in the second case, I have 2 nonmetals, 1 phosphorus and 3 bromine atoms. In this case, we will need to look up the electronegativity values to decide on the order in the formula. Phosphorus is 2.1 and bromine is 2.8. And since phosphorus is less electronegative, it's listed first. The formula then is PBr3, since there are 3 bromine atoms. Last example here, I have 2 chlorines and 1 magnesium atom. So chlorine has electronegativity of 3.0, magnesium was 1.2, magnesium is listed first, MgCl2. However, once again, you would probably, or should probably, recognize this as an ionic compound made of a magnesium metal cation and a chlorine or chloride nonmetal anion, and so you would know automatically that magnesium would precede chlorine in the formula. So this is stated again here in formulas of ionic compounds. Symbols of metals precede nonmetals because all metals have lower electronegativity values than any nonmetal on the table. So some practice here. How about use the table of electronegativity values to write the chemical formulas of the compounds shown. So in the first example, I have 2 aluminum and 3 oxygens shown. Looking on the table, or knowing that aluminum is a metal and oxygen is a nonmetal, you would know that aluminum is less electronegative than oxygen and would be written first, and you'd write Al2O3. This next molecule, I have an OCO, 2 oxygens and a carbon. Well, we need the electronegativities in this case. Carbon's less electronegative, it's written first, and that's CO2, good old carbon dioxide. And finally, I have CaF2. Calcium is less electronegative than fluorine because calcium's a metal and fluorine's a nonmetal, so it's written CaF2. Now, there are some exceptions in chemical formulas, and we'll deal with a couple of them right now. The least electronegative atom in binary compounds are usually listed first, but there are a few historical exceptions. Take a look at these 2 molecules. These are hydrocarbon compounds. We would abbreviate these as simply HC. They are compounds that contain only hydrogen and carbon. Now, carbon, we know, has an electronegativity of 2.5, but it's listed before hydrogen in hydrocarbon formulas, even though carbon has the higher electronegativity value. So in this case, it's written as CH4 instead of H4C. This compound is called methane. It's the major component of natural gas. The one to the right of it, C2H6, is ethane. and it's the second largest component of natural gas. So again, these are called hydrocarbons. They're compounds that contain only hydrogen and carbon. In such compounds, carbon is listed before hydrogen, even though it's more electronegative than hydrogen. So it's just one of those exceptions. There is some argument that can be made for this, and I'll try and present one here. In most formulas of binary compounds in which hydrogen is listed first, well, most of them are acids, such as hydrochloric acid, HCl, hydrofluoric acid, HF. But hydrocarbons are not acidic. Their hydrogens are not acidic hydrogens, and so they're not listed first. The hydrogens are listed last, and perhaps that's the reason, is to avoid confusion. Another exception that we see in chemical formulas of binary compounds involves nitrogen. In formulas of binary compounds containing nitrogen, you'll see that the N atom is usually listed first regardless of its electronegativity value. Here's two examples. The first compound on the left is ammonia, NH3. Notice that nitrogen is listed first in the formula, even though it's more electronegative than hydrogen, yet it's written first. In the example on the right, we have N2O5. In this case, nitrogen is less electronegative than oxygen, and it is written first. So regardless of whether the nitrogen is more or less electronegative, in binary compounds, nitrogen is generally listed first. Now, another justification perhaps, in the case of ammonia, NH3, it's not acidic. Listing the hydrogens first might be confusing. In fact, ammonia is a moderate base. If we listed hydrogen first, it would make ammonia look acidic. H3N looks like an acid, but ammonia is not acidic in any case. All right, so enough for the exceptions. Let's name some binary compounds. Now, there are three systems for naming binary compounds. The stock system is the most comprehensive system. An example that you're familiar with is sodium chloride. We have the prefix system. It's used for non-metal compounds only. Some examples you probably are familiar with is carbon monoxide and carbon dioxide. The prefixes mono and di involve the prefix system. And the third system is called the us-ic system. It has limited use, and it's quite easy to grasp. Here's an example. You may have heard the terms ferrous oxide and ferric oxide, and there are those suffixes us and ic as used in that system. So first of all, the stock system for naming binary compounds. CaCl2 is calcium chloride. So the name of that compound, calcium chloride, is a stock system name. Calcium chloride, by the way, is road salt. It's a de-icer used in winter. In the stock system, the name of the less electronegative atom is written first, followed by a space, and then the name of the more electronegative atom is listed last, and the ending is changed to IDE. So in the case of chlorine, the ending must be changed to IDE, chloride. Here's another example. Al2O3 is named aluminum oxide. Again, we have the name of the less electronegative atom first. That name is exactly the same as the atom's name on the periodic table, followed by a space, and then the name of the more electronegative atom, but the name of the atom has to be changed so it ends in IDE. So in the case of oxygen, that's oxide. So, anionic compounds made of metal cations, which are positive, and nonmetal anions, which are negative, the less electronegative atom is a metal cation, and the more electronegative atom is a nonmetal anion. The name of the metal cation is the same as the element's name, but the anion's name ends in IDE. Note that the stock system name does not tell us the relative number of atoms in the formula. For instance, calcium chloride does not tell us that there's one calcium and two chlorides. This will be explained later. We need to learn, that is, you need to learn, the anion names and their charges. Now, the process or system is that non-metal anions gain enough electrons to fill their valence shell, their outermost electron shell, to become isoelectronic with the nearest noble gas. In the case of hydrogen, well, the nearest noble gas is in group 8A. It's helium with 2 electrons, so it would gain just 1 more electron. And when it gains an electron, a negative charge, it takes on a charge of -1, and it's now called hydride. The ending is IDE. Let's move to the next nonmetal, carbon. Carbon's anion would be carbide with a charge of -4. I'm going to use the word charge and oxidation number interchangeably. Even if they're not exactly the same, we use them that way in nomenclature. Why is it -4? Well, carbon would need to gain 4 electrons, 1, 2, 3, 4, to become isoelectronic with the nearest 8A element, neon. Nitride is in group 5A. It'll need 3 electrons to become an anion, like group 8A anion, so -3 would be the charge of the anion of nitrogen, which is nitride. The same can be said for phosphorus. Its anion will be phosphide, again with a charge of -3 for the same reason as nitrogen. As we move to group 6A, we have oxygen, sulfur, and selenium. What would be their anion names and charges? Well, oxygen becomes oxide, and of course its oxidation number or charge must be -2, because this atom will gain 2 electrons to be an anion, becoming isoelectronic with a group 8A element. Similarly, sulfur would become sulfide with a charge of -2, and selenium would become selenide with a charge of -2. The group 7A elements, when they become anions, fluorine becomes fluoride, would need only 1 electron, 1 negative charge to become isoelectronic with the nearest noble gas. Chlorine is chloride, -1. Bromine becomes bromide, -1. Iodine becomes iodide. So anions typically have only 1 possible oxidation number, and it's easy to learn if you know their group number on the periodic table. All right, let's get some practice naming these binary compounds using the Stokes system. Now, I'll go through these fairly quickly, but you can pause the video as needed to figure out the answers. The first one is potassium phosphide. Next, we have MgO is magnesium oxide. Al2S3 is aluminum sulfide. Ca3N2 is calcium nitride. MgF2 is magnesium fluoride. LiI is lithium iodide. Be2C is beryllium carbide. BaBr2 is barium bromide. CaH2 is calcium hydride. Na2Se is sodium selenide. SrCl2 is strontium chloride. B2O3 is boron oxide. SiC is silicon carbide. And HF is hydrogen fluoride. So note that the last 3 examples, B2O3, SiC, HF, these are not ionic compounds. In fact, they are composed of metalloids and or nonmetals only. And yet the Stokes system names all compounds as if they were ionic. The less electronegative atom is first using the atom's name as found in the periodic table, like potassium, magnesium, aluminum, etc. The more electronegative atom is written last using the IDE ending, phosphide, oxide, etc. How about writing chemical formulas for binary compounds? Well, to write the chemical formulas and name compounds, you can't escape it. You'll need oxidation numbers of atoms or ions in a compound. Now, oxidation numbers are explained in detail in a video entitled Oxidation Numbers that's posted on YouTube, and they'll only be discussed briefly in this lesson. So what is an oxidation number? Oxidation number is a charge that's assigned to an atom or an ion in a compound. Now, all pure elements have an oxidation number of 0. For example, copper metal, has no charge. It has an oxidation number of 0. The element hydrogen has no charge, oxidation number of 0. And sulfur, octasulfur in this case, oxidation number 0. That's the case for all elements. There's about 20 elements that have only one oxidation number or fixed oxidation number other than the 0 that they all have. So these fixed oxidation numbers must be memorized, but again, it's easy to do if you learn their position on the periodic table. And then the oxidation number of the other atoms or ions in a formula or a name are calculated using the known values. So here is a periodic table that lists the most common oxidation numbers of the elements. Those elements, about 20 of them that have fixed oxidation numbers, are highlighted red and yellow on the table, as for example here, group 1A. You'll notice that metals cannot have negative oxidation numbers. They're always positive. If you scan the values, you'll see no negative values for metals. That's because metals can only lose electrons to become isoelectronic with the nearest noble gas and never gain. Now you'll notice, however, that most nonmetals can have negative or positive oxidation numbers. For example, chlorine in the compound ICl, chlorine has a negative oxidation number of -1, but in ClF, it has an oxidation number of +1, and in ClO2, chlorine's oxidation number is +4, and in ClF7, it's +7. Only one possible negative oxidation number for anions, but often multiple possible positive oxidation numbers. You'll also see that in covalent compounds, the nonmetal that has the higher electronegativity value, like fluorine in ClF or oxygen in ClO2, the nonmetal with the higher electronegativity value always gets the negative oxidation number. So the fixed oxidation numbers are easily memorized by knowing their A group number on the periodic table. So let's spend a minute and look at that. So let's look at group 1A, the metals lithium, sodium, potassium, rubidium, and cesium, and francium, which is not shown here. Note their oxidation number is only and always +1 in all their compounds. It's easy to remember they're in group 1A, as is silver always +1, which by the way is in group 1B. Now what about hydrogen? Well, it can also be +1 like the metals in group 1A, but of course it can be -1 if it's going to be an anion, in which case it becomes like helium. Group 2A metals, beryllium, magnesium, calcium, strontium, barium, and radium below it, their oxidation number or charge is always +2 in all of their compounds, no exceptions. And in group 2B, zinc and cadmium, +2 as well, always. In group 3A, we have boron, aluminum, and gallium. Their oxidation numbers of +3 are fixed, always +3 in all their compounds. In group 4A, we find silicon and germanium. These two metalloids, their oxidation numbers are always +4. In group 5A, 6A, 7A, I guess we've already discussed, we can easily calculate the oxidation number of the anion by figuring out how many electrons an element would need to become isoelectronic with the nearest noble gas. For example, nitrogen in group 5A needs 3 electrons, 1, 2, 3 to become isoelectronic with group 8A. 2 electrons for each anion in group 6, 1 electron for each anion group 7. And as we stated earlier, the nonmetals can also have multiple positive oxidation numbers, and these would have to be calculated from the known oxidation numbers in any given compound. All right, so writing the formula of binary compounds. You need to remember that the chemical formula represents the smallest whole number ratio of atoms or ions in a compound. The positive and negative charges, or oxidation numbers, must add to be 0, or we sometimes say they balance. What we mean is the total positive charge equals the total negative charge. They have the same magnitude. +2 and -2. +3 is -3. +4 balances -4. There will always be the same positive and negative charges in a compound. So let's break it down in some steps here. First of all, we'll look at calcium chloride. If we want to write the formula, first step is to obtain the ion symbols and their oxidation numbers, or charges as they're sometimes called. Calcium is in group 2A. Its charge is always +2. Chloride's in group 7A. It has to be -1. Secondly, we find the total charge needed to balance the positive and negative charges. In other words, we have to have total positive and negative charges equal. We can see that calcium is +2, and each chloride is -1, which means we need 2 of them to balance the charges. Then we find the ratio of positive and negative ions. So for every 1 calcium ion, you'd need 2 chloride anions. And then the formula is written with subscripts. It would be CaCl2. How about the next one? Boron bromide. We need the symbols and oxidation numbers. Well, boron is always +3, and bromine as an anion is Br-1, bromide. Now I've listed the oxidation numbers here because neither of these are metals. We have a metalloid and a non-metal, so to list which one goes first, we need to have the electronegativity values. The charges, boron is a fixed value of +3 in group 3A, bromide is -1, so we need 3 bromide ions for every 1 boron +3 cation. There's our ratio. And the subscripts in the formula tell us Br3 would be the formula. How about hydrogen sulfide? The ion symbols and their charges. Well, hydrogen is H, and of course it's going to be either +1 or -1, as we saw. If it's the less electronegative atom in the compound, then it would take its positive oxidation value, and it is in this case less electronegative. Sulfide is more electronegative, and so it uses its negative oxidation number. Since it's in group 6A, it has to be -2. Hydrogen, each hydrogen ion is +1, and each sulfide is -2. We're going to need 2 hydrogen +1 ions to balance charge. 2 hydrogen ions for every sulfide -2 ion, and so the formula is H2S. Hydrogen listed before sulfur because hydrogen is less electronegative. In the last example, we have magnesium phosphide. Magnesium is in group 2A, hence its charge is only ever +2. Phosphorus is in group 5A, and therefore its anion would gain 3 electrons to become like a group 8A anion. Phosphide has to be -3. In this case, we can't directly balance charge. We have an odd number and an even number. We need to find the lowest common multiple of odds and even numbers, and that would be 6. If I had 3 magnesium +2 ions, the total positive charge is +6. And if I had 2 -3 phosphide anions, the total negative charge would be -6. That would balance the charges. So 3 magnesium +2 ions for every 2 phosphide -3 anions. And the formula, therefore, is Mg3P2. So nonmetals, such as chlorine, bromine, hydrogen, sulfur, and phosphorus, can have either positive or negative oxidation numbers. An atom is assigned a positive oxidation number when it is the less electronegative atom in a compound. And a negative oxidation number is assigned when it is the more electronegative atom in a compound. So let's do a little practice here. Recommend that you write the formulas of the ions and their charges before you actually write the formula of the compound. So in the first case, magnesium in group 2A, Mg plus 2, oxide in group 6A, negative 2, and therefore they combine in a 1-to-1 ratio of MgO. The lowest whole number ratio that satisfies the charge is the formula. Now again, I'm going to move through these fairly quickly. You can pause the video if you need to. Potassium is plus 1, it's group 1A. Nitrite is in group 5A, therefore a negative 3 anion, K3N. Barium is in group 2A, so it's plus 2. Fluorine is in group 7A. As an anion, it must be minus 1, so BaF2. Silicon, group 4A, is plus 4. And iodide in group 7A as an anion has to be minus 1, SiI4. Beryllium carbide, beryllium's in group 2A, therefore it's plus 2. And the anion of carbon in group 4A has to be negative 4, carbide, so Be2C. Notice again, you need to get the lowest ratio that satisfies the charge. That's 2 berylliums for each 1 carbide. Calcium hydride, calcium's plus 2, hydride is negative 1, CaH2. Lithium selenide, lithium's in group 1A, so it's plus 1. Selenium's in group 6A, so its anion must be minus 2. We'll need 2 lithiums for each selenium, Li2Se. Sodium phosphide, sodium's in group 1A, phosphorus in group 5A, hence the charge is plus 1 and negative 3, Na3P. Zinc phosphide. Now zinc is one of the elements with a fixed oxidation number. It's in group 2B. It's always plus 2. Phosphide is in group 5A, negative 3. Hence Zn3P2 is the lowest whole number ratio in which the charges will balance. 3 plus 2 charges will be plus 6. 2 negative 3 charges will be minus 6. Whenever you have an odd and even oxidation number other than 1, it gets a little more complicated. We'll deal with it in just a moment. Aluminum sulfide, Al plus 3 because it's in group 3A, S minus 2 because it's in group 6A, Al2, S3, so 2 times plus 3 is a total positive charge of plus 6. 3 times negative 2 is a total negative charge of minus 6. Positive and negative charges must balance or be equal, and that's the formula, Al2S3, that does it. Boron oxide, it's in group 3A, hence it's plus 3. Oxygen in group 6A, negative 2. B2O3 is the formula. So again, the chemical formula shows the lowest whole number ratio of ions such that the total positive and negative charges are equal. Now, the inverse rule is an easy way to find this ratio, particularly if it's complicated as it was in the last 3 examples. Let's consider zinc phosphide. Zinc has a plus 2 charge, phosphide is negative 3. Its formula is Zn3P2. How do we obtain that? Well, it turns out that the charge of one anion is the multiplier of the other anion. So negative 3 for the phosphide tells me there must be 3 zinc ions. Likewise, the charge of the cation becomes the multiplier of the anion. That tells me the plus 2 charge on zinc tells me there are 2 phosphides. And this ratio will always balance the charge. Zn3P2. The number of zinc cations, 3, right here, equals the charge of the anion, negative 3, and the number of the phosphide anions, which is 2, equals the charge of the cation. It's called the inverse rule. Just cross those charges over and make them into multipliers. Change them from superscripts charges to subscripts. But you have to remember to reduce this to the lowest whole number ratio. Take, for example, beryllium carbide. See, beryllium is +2 and carbide's -4. If you simply use the inverse rule, you would write Be4C2. Anytime you have two even multipliers, reduce them to the lowest whole number ratio that you can. If you're going to use the inverse rule, remember to reduce to the lowest whole number ratio when you're done. All right, we next have to learn how to find the oxidation number in compounds that contain a multivalent ion. A multivalent ion is one that has more than one oxidation number. So, for example, simple example to start with, water, H2O. It's not HO2, it's not H3O, it's not HO, etc. Why? Well, because the oxidation number of hydrogen is +1 and the oxidation number of oxygen is -2. We can work it out. Now, in order to combine elements in a chemical formula in the correct ratio, you need to know the oxidation numbers of each element. You'll also need to know the oxidation numbers for writing chemical names. However, many elements are multivalent. They don't all have fixed oxidation numbers. A number of them have more than one possible oxidation number. Fortunately, it is always true that at least one of the elements in a binary compound will have an oxidation number that is known for sure, it's fixed, and so the other element's oxidation number can be calculated. The first example, manganese has 5 different oxidation numbers that appear in its compounds. You sometimes see +2, +3, +4, +6, or +7. Calculate the oxidation number of manganese in MnCl2. The answer is +2, but how do we get this? Well, the oxidation number of chloride is -1 because it's in group 7A and it's more electronegative than manganese, so it always will use its value of -1, it's group 7A, as an anion. The total negative charge of the two chlorides is 2 times -1, which is -2. And so the total positive charge of the manganese has to be equal +2. And so the oxidation number of manganese is +2. Okay, in this next example, we are asked to calculate the oxidation number of manganese in Mn2O3. And the answer is that manganese is +3, but here's why. You see, the oxidation number of oxygen is always -2, and the total negative charge is -2 times 3, since there are 3 oxygens, for a grand total of -6. And so the total positive charge for both manganese ions must be +6, because the total positive charge is equal to the total negative charge for neutral compounds. This compound is neutral. There's no charge shown on it. And so each manganese has a charge of +6 divided by 2, or +3. So we take the total positive charge divided by the number of manganese atoms or ions in the formula and get the charge on each one, in the same way that you took the charge of each oxygen and multiplied it by the number in the formula to get the total negative charge. You can solve this as a math equation in a video that I previously posted on YouTube, calculating oxidation numbers. I do more examples of this. We're going to let the oxidation number of manganese be X in Mn2O3. We're going to say the sum of all the oxidation numbers is 0 because there is no charge shown in the formula. So X oxidation number times 2 plus -2 for each oxygen times 3 equals 0. And solving for X, we get that X is equal to 6 divided by 2, or +3. So manganese has a charge of +3. A little bit tedious. Here's an easier way. Use the inverse rule. You can say that the number of manganese atoms is equal to the charge of each oxide, and similarly the number of oxygen anions is equal to the charge of each manganese cation. Alright, so here's some practice. Calculate the oxidation number of the underlined ion in each formula. We'll start by writing the anion charge, since it's fixed and it's known, oxygen's -2, and there are 2 of them, so manganese must be +4. In the case of MnO3, oxide's -2, and there are 3 of them, total positive charge must be +6. In the case of Mn2O7, there are 7 times 2, or -14 negative charges, so the total positive charge must be +14 divided by 2, or +7, or simply use the inverse rule in reverse. V3N5. Well, nitride is -3, and there's 5 of them, so -15 is the total negative charge. Divided by 3 gives a total positive charge of +5 for each vanadium. Carbide is -4, and there are 3 of them, for a total of -12 for the anions, and divide that by 4 gives +3 for each iron ion. In the case of Cu3P, phosphide is in group 5A, therefore it's -3. Each copper must be +1. Fluoride is in group 7A, so it's -1, and there are 4 of them, so lead must be +4. Chloride is in group 7A, so it's -1, and there are 5 of them, so phosphorus must be +5. Sulfide is in group 6A. That's -2 for each sulfide, times 5 is -10, divided by 2 is +5 for each molybdenum. And hydride is in group 1A, so it's -1 is an anion, and there are 3 of them, so nickel must be +3. All right, naming binary compounds containing a multivalent ion. So iron, like manganese, can exhibit more than one oxidation number. There are in fact 2 kinds of iron chloride. There's FeCl2 and FeCl3. And so the name iron chloride is ambiguous. It shouldn't be used. Here's a picture of those 2 types of iron chloride. Iron 2 chloride is green, and iron 3 chloride is a yellow, rusty colored. And each distinct chemical must have a unique, unambiguous name. In binary compounds that contain cations with more than one oxidation number, then the oxidation number of the cation is written in Roman numerals in parentheses immediately after the cation. So FeCl2 is named iron 2 chloride, and FeCl3 is named iron 3 chloride. Here it is laid out. The charge or oxidation number of the cation is listed in Roman numerals in the name. Immediately following the name, no space. In the case of iron 3 chloride, well, that 3 is the charge of the iron cation. Now, since we're going to be using Roman numerals, you have to know some Roman numerals, just a few, 1 to 8. Letter the English or Arabic number 1, it looks like a capital I or a stick. 2 is 2 sticks, and 3 is 3. 5 is V. 1 to the left of V is like 5 minus 1 is 4, and 1 to the right of V is 5 plus 1 is 6, 7 is 8, and that's the highest oxidation number we will encounter in standard chemical formulas. Look at the formulas and the names of 2 kinds of iron oxide. There's FeO and Fe2O3. Now FeO is black, and Fe2O3 is a rusty red color. Here again, look at the oxidation numbers and look at the names and the formula. So the oxidation number, either 2 or 3, it indicates the charge on the ion, not necessarily the number of anions present. So you want to be careful here. Sometimes students try to find shortcuts, and sometimes that's good and sometimes it's not so good. So students sometimes think, well, the oxidation number plus 3 tells me how many of the other ion are in the formula. Well, sometimes that works, like in the case of iron 3 oxide. But notice it does not work here. The oxidation number of 2 is not the same as the number of oxygens in the formula. So, please note carefully the oxidation number listed immediately after the cation in the name indicates the charge on the cation and not necessarily the number of anions in the formula. So to name a compound, write the ion symbols and determine their oxidation numbers from the combining ratio given in the formula. The anion usually has only one possible oxidation number. So calculate the oxidation number of the cation, remembering that the total positive charge and negative charge in a compound are equal. Alright, so here's a step-by-step procedure for naming binary compounds that contain a multivalent ion. Take, for example, Au3N. Step 1 is to identify the oxidation number that is known for sure. That's usually the anion's oxidation number. Well, in this case, nitrogen, or nitride, is more electronegative than gold, since it's a nonmetal, so it's going to use its negative oxidation number, which is -3. We know that for sure. If you're allowed, you can check the periodic table for possible charges of the other ion. What I mean by allowed is, if you're simply taking one course in chemistry, you're often provided with a periodic table that contains a lot of oxidation numbers on it. But if you're studying chemistry, you'd be expected to calculate this without the aid of a table. In any case, you'll find that gold is either +1 or +3 if you look on a table. Next, you want to determine the ratio of ions in the formula. Well, Au3N means that there are 3 gold ions for every 1 nitride ion. Then you want to find what charge must be on the multivalent ion to balance all the charges. Well, since nitride is -3, and there are 3 gold ions, each one must be +1, such that the total charges are equal. So we need 3 gold +1 ions for every 1 nitride -3 ion. Write the name of the compound. It would be gold 1-nitride, where 1 is the oxidation number of the multivalent cation. How about Cl2O5? Once again, we're going to identify the oxidation number that is known for sure. Oxygen is more electronegative than chlorine. Oxides in group 6A. Its oxidation number is -2. If you're allowed, you can check the periodic table. The possible positive charges of chlorine are +1, +3, +5, +7. Now we know it can be -1, but not when it's combined with a more electronegative element. It's got to use a positive oxidation number here, and these are the possibilities. The ratio of ions is determined from the formula. There are 2 chlorines for every 5 oxides. Now let's find what charge must be on the multivalent ion to balance all the charges. Well, oxides -2, and there are 5 of them in the formula, so that would be -10, total negative charge. Total positive charge is equal, that's +10, divided by 2, since there are 2 chlorines in Cl2O5, and each one therefore is +5. Hence, the formula is chlorine 5 oxide. Let's get some practice naming binary compounds that contain a multivalent ion. Suggest that you write the symbols and charges of the ions first. We're going to determine the oxidation number of the ions in the compounds below, and we'll use those oxidation numbers to write the stock system names of the compounds. In the first case, oxides -2, therefore iron must be +2, it's iron 2 oxide. In the next example, CrO3, well, oxide is -2, and there are 3 of them, therefore chromium must be +6, chromium 6 oxide. And NiF3, fluoride is -1, and there are 3 of them, so nickel must be +3, hence nickel 3 fluoride. The next example, oxygen is -2, so copper must be +2, hence that's copper 2 oxide. In Cu2O, oxygen is -2, and there are 2 coppers, so each one must be +1, that would be copper 1 oxide. AuBr3, bromide is -1, there are 3 of them, so gold must be +3, we would write gold 3 bromide. Fe2O3, oxide is -2, and there are 3 of them. That's -6. Total positive charge is +6. Divided by 2 is +3. Or we could simply use the inverse rule backwards. O minus 2, Fe plus 3. That's iron 3 oxide, also known as rust. Sulfide is -2, and there are 2 of them, so manganese must be +4. That is named the manganese 4 sulfide. COCl3, we know that chloride is -1, and there are 3 of them, so cobalt must be +3. That's cobalt 3 chloride. Oxide's -2, so cobalt must be +2. That is named cobalt 2 oxide. Nitride is -3, and there are 4 of them for a total negative charge of -12. +12 divided by 3 is +4, or simply use the inverse rule backwards. That would be tin 4 nitride. Similarly, since tin is going to be +2 in this example, that would be tin 2 nitride. This time we'll go the other way. We'll start with the name and go to the formula. In the first case, chromium 3 oxide, we're told from the name that chromium is +3, oxide is -2. We can use those charges and the inverse rule to calculate the formula Cr2O3. Nickel 2 fluoride tells us nickel's +2, fluoride's -1. The formula is NiF2. Titanium is +4, oxide's -2, and the ratio will be TiO2. So be careful here. If you use the inverse rule, you'll get Ti2O4, which needs to be reduced to the lowest whole number ratio. The name tells us that cobalt is +3 and phosphide is -3, and hence 1-to-1 ratio, COP would work. Vanadium 5 chloride tells us vanadium is +5, chloride's -1. We'll need 5 chlorides for every vanadium, VCl5. And tungsten is +4, carbon is -4, 1-to-1 ratio, WC is the formula for tungsten 4 carbide. So notice that the formulas that we wrote of binary compounds do not show the charge of the cation or the anion. So don't write charges in the formulas. Do not carry these charges into the formulas. And as a reminder, think of something you know. Sodium chloride's formula is NaCl, not Na plus Cl minus. Right, next we want to look at binary acids. Now, a binary acid contains hydrogen that is covalently bonded to a nonmetal. Hydrogen chloride, HCl, is an example of a binary acid. Now, when it dissolves in water, hydrogen chloride is named hydrochloric acid. Why? Well, because it releases an acidic hydrogen ion as it ionizes in water. So you need to learn the names and the formulas of the 5 common binary acids listed below. For HF, the anhydrous name is hydrogen fluoride. That means anhydrous means in absence of water. Without water present, this would be called hydrogen fluoride. But when it's placed in water, it's called hydrofluoric acid because it ionizes according to this reaction, releasing a hydrogen ion and a fluoride anion. HCl, anhydrous name is hydrogen chloride, and in water it's called hydrochloric acid because it ionizes as shown. HBr is named hydrogen bromide, but when it's in water it's hydrobromic acid, again because it ionizes as shown. HI is hydrogen iodide, and in water it's hydroiodic acid. Sometimes just the first O is dropped and it's hydriodic acid. You have an option there. It ionizes as shown. And finally, H2S is a diprotic acid. It's got 2 ionizable hydrogens. Hydrogen sulfide is the name. Now be careful here. The name in water is called hydrosulfuric acid, not to be confused with sulfuric acid, which we'll discuss later. and there's hydrosulfuric acid liberating 2 hydrogen ions and it's producing a sulfide anion. So here's a summary of the stock system nomenclature for binary compounds. Look at compounds like tin 2 oxide and tin 4 oxide, chromium 3 oxide, chromium 6 oxide, copper 1 bromide, copper 2 bromide. What am I saying here? Well, you can see that there's more than one tin oxide, there's more than one chromium oxide, there's more than one copper bromide. You see tin, chromium, and copper all have more than one oxidation number. In the case of tin, it's 2 and 4, chromium is 2, 3, and 6, copper is 1 and 2. So the rule is that oxidation numbers must be included in the name written in Roman numerals whenever there's more than one oxidation number in a compound. Otherwise, it is ambiguous. On the other hand, names like sodium chloride, calcium chloride, aluminum oxide, zinc sulfide, etc., there's only one sodium chloride, there's only one calcium chloride, and one aluminum oxide, etc. Sodium, calcium, aluminum, zinc, and silver all have only one oxidation number. Sodium and silver are +1, calcium and zinc are only +2, aluminum is +3. The point is, the oxidation number is not stated in the name. You would never say calcium 2 chloride or sodium 1 chloride. Next, we want to look at the prefix system for binary compounds. This is a lot simpler. You'll appreciate this one. So we use the prefixes to state the number of atoms present in a compound. So it's restricted to binary compounds containing 2 nonmetals. The prefix is Latin or Greek. It's attached to the name of an element to indicate the number of atoms present of that element in the compound. So for 1 is mono and 2 is di and tri, tetra, penta, hexa, and so on. So let's look at some examples using the prefix system. CO is named carbon monoxide, and CO2 is named carbon dioxide. Perhaps these are familiar to you. SO3 is named sulfur trioxide. CCl4 is named carbon tetrachloride. PCl5 is named phosphorus pentachloride. And SF6 is named sulfur hexafluoride. What happens if you have 7, 8, 9, or 10? It occasionally happens. The prefixes are hepta, octa, enea, and deca. Now I have to refine this formula a little bit further. Although the system is used almost exclusively for non-metal compounds, occasionally it is used when a metal is present. Now, very important here, we attach a prefix to the second atom in the formula always. Notice we put monooxide, dioxide, trioxide, tetrachloride. In every case, we attach a prefix to the second atom in the formula, always. But we attach a prefix to the first atom in the formula only if there's more than one of them, which is why I didn't attach any prefixes to these, because there's only one of the first atom in every case. Here's some examples to work on. I want you to name these by both the stock system name and the prefix name. So we have N2O is dinitrogen monoxide. Notice we use the prefix in front of the first atom's name because there is more than one of them. In the stock system, that would be nitrogen 1 oxide, because oxide's -2, each nitrogen must be +1. Next example is simply nitrogen monoxide, which would be nitrogen 2 oxide. Next example would be nitrogen dioxide, and we can calculate the oxidation number of nitrogen to be nitrogen 4 oxide in that example. Here is another example where you have more than one of the first atoms, so we need to state how many, and that would be dinitrogen trioxide. Using the inverse rule, you could figure out the oxidation number of nitrogen in N2O3 is 3, so that's nitrogen 3 oxide. Now here's an interesting formula. At first glance you say, well, that should be reduced. to NO2, dividing by 2. That is normally the case. This is a rare exception. NO2 is different than N2O4. They both exist. They actually can interchange, but they are different. So we're going to keep it as N2O4. We would name that as dinitrogen tetraoxide. Now the A here is optional, which is why I put it in parentheses. So either leave it in and just say tetraoxide, or take it out and say tetroxide, but don't use the brackets in the parentheses in either case. Now what about the stock system name? Well, if you work it out, that's nitrogen 4 oxide. Now you say, wait a minute. NO2 is nitrogen 4 oxide and N2O4 is nitrogen 4 oxide. So here's an example where two different compounds actually have the same stock system name. That's redundant. We can't have that. And so this is an example where the prefix name is important. It actually distinguishes between these two different compounds, nitrogen dioxide and dinitrogen tetroxide. Next one is dinitrogen pentoxide or pentaoxide. Don't use parentheses. That's nitrogen 5 oxide. Here is iodine monochloride, iodine 1 chloride. This is carbon disulfide, which is carbon 4 sulfide. Here is sulfur dioxide, which is sulfur 4 oxide. This is phosphorus trichloride, phosphorus 3 chloride. Next we have diphosphorus pentaoxide. Again, don't use parentheses. Either use the A or drop it. It's either pentaoxide or pentoxide, your choice. Or it's phosphorus 5 oxide. Here's sulfur hexachloride or sulfur 6 chloride. And here's one example of a ionic compound named by the prefix system. It shouldn't really be done, but it is in popular use, so I present it here. No problem. It's manganese dioxide. The proper name is manganese 4 oxide. And finally, we have the us-ic system. Very short, very simple. For binary compounds in which the cation has only 2 oxidation states, this old us-ic system is sometimes used. And in a few cases, when the English name of the metal atom is awkward to attach us or ic to it, the Latin name of the metal is used instead. So the suffix us is added to the lower oxidation number, and the suffix ic for the higher oxidation number. Now copper has 2 oxidation states, so it's a candidate. The Latin name is cuprum, and so the lower oxidation state, copper 1, is named cuprous, and copper 2 is cupric. Iron, Latin name is ferrum, has 2 oxidation states. Iron 2 is named ferrous, and iron 3 is named ferric. Lead has the Latin name plumbum, which is comes from, I suppose, in English, plumbers used to use lead piping for drain, waste, and vent pipes. In any case, lead has 2 oxidation states, lead 2 and lead 4. The lower one is named plumbus, and the higher one plumbic. Likewise, tin has the Latin name stannum, and so it's also in group 4A, right below lead. It has the same oxidation states, +2 and +4. The lower one is stannous, and the upper one is stannic. The last Latin example that I'm aware of is for gold. Gold has the Latin name aurum. It has 2 oxidation states, +1 and +3. The lower oxidation state is aurus, and the upper oxidation state is auric. I suppose somebody decided that gold us and gold ic was too awkward to say. Here's a few examples of divalent cations whose English name is just fine. So we have mercury 1 and mercury 2, mercurous and mercuric, respectively. Platinum 2 and platinum 4, we have platinous and platinic ions. And cobaltus and cobaltic correspond to cobalt 2 and cobalt 3, respectively. Let's get some practice. using the us-ic system to name binary compounds. Now, in order to use the us-ic system effectively, you would need to know the two oxidation states of the atoms involved. I'm going to ask you to write the stock system name first, followed by the us-ic system name. PbCl2. Now lead is in group 4A and has two oxidation states. It's either +2 or +4. This first example is lead 2 chloride, and that's the lower oxidation state. Therefore, that's plumbous chloride. PbCl4 is lead 4 chloride, and that would therefore be plumbic chloride. Now, tin is directly below lead on the periodic table, group 4A. It has the same oxidation states. This first example is tin 2 bromide, hence that is stannous bromide. The higher oxidation state compound is tin 4 bromide, which therefore is stannic bromide. Now, copper has two oxidation states, +1 and +2. The first formula is copper 1 oxide, and therefore that would be called cuprous oxide. The second formula, CuO, is copper 2 oxide, which thus is called cupric oxide. Iron commonly has only two oxidation states, iron 2 and iron 3. FeO is iron 2 oxide, hence the us-ic name is ferrous oxide. Fe2O3 is iron 3 oxide, and that then is ferric oxide. Now, gold has two oxidation states, +1 and +3. In this example, gold is in its +3 oxidation state, hence that's gold 3 sulfide, and that would therefore be called auric sulfide. Platinum has two oxidation states, +2 and +4. This first example, PtF2, is platinum 2 fluoride, hence platinous fluoride. PtS2 has platinum in its +4 oxidation state. That's platinum 4 sulfide, hence platinic sulfide. Mercury has two oxidation states, +1 and +2. In this first example, you can see mercury is in its +1 oxidation state. Hence, we have mercury 1 carbide, also known as mercurous carbide. And finally, we have Hg3N2. We can see, using the inverse rule, the oxidation state of mercury is +2. Hence, that's mercury 2 nitride, also known as mercuric nitride. I want to speak last about peroxides. There's a reactive type of compound called peroxides that has important commercial and industrial applications. You will encounter it in your laboratories, no doubt. The most familiar example is probably hydrogen peroxide, H2O2. So compare, if you would, the formula and structure of water versus peroxide. The stock system name of water would be hydrogen oxide, and the stock system name of H2O2 therefore would be hydrogen peroxide. The prefix per says one more oxygen than the normal form. Peroxides have this oxygen-to-oxygen single bond. They are one of the strongest oxidizers known. A 30 to 50% aqueous solution of peroxide, well, they're used industrially to bleach pulp and paper. During the First World War, concentrated peroxide solutions were used to propel torpedoes. They quickly decompose in the presence of a catalyst, releasing steam and oxygen quite violently. Peroxide solutions up to 12% in water are used to bleach hair, usually along with some ammonium hydroxide. And 3% aqueous solutions is sold in the pharmacy as a household disinfectant for cuts. So we see them around. Now, peroxides are indeed unusual in that the oxygen in a peroxide has an oxidation number of only -1. And so the formula of peroxide is written as O2 negative 2. That's because the peroxide anion is bonded as a pair of oxygens, and they always occur together or it's not a peroxide, so we write them as O2 with a charge of negative 2. Now, you will recall that oxygen is in group 6A, and it's only stable when it gains 2 electrons and becomes oxide O-2. So it's not surprising that peroxide O2-2 is so reactive, so unstable. The group 1A and 2A metal peroxides have some interesting applications, which I'll mention briefly here. For example, sodium peroxide, Na2O2, converts carbon dioxide to oxygen and sodium carbonate according to this reaction. So notice that just add these together, you get sodium carbonate and oxygen is released. Now I have a fractional coefficient in front of the oxygen just to simplify so you can follow it easier, but we know to display it properly you should multiply all of these terms by 2 to remove it. Both lithium peroxide and sodium peroxide have been used to regenerate oxygen from air that's been exhaled by people in confined spaces like in submarines and spacecraft. So let's get a little practice here. The first compound, of course, is water, but the stock system name is hydrogen oxide. The prefix name is dihydrogen monoxide. Okay, what about H2O2? What's the stock system name of that? Well, that's hydrogen peroxide. Notice the O2 negative 2 anion. Can you write the formula barium peroxide? Well, let's write the symbols and charges. Barium's plus 2, peroxide's O2 minus 2. They'd combine in a 1-to-1 ratio, so BaO2 is the correct formula. Well, how about potassium peroxide? Potassium's plus 1, O2 is minus 2. We'll need 2 potassiums, so K2O2 is the formula of potassium peroxide. And let's compare that to the normal oxide of potassium. That's simply potassium oxide, K2O. And how about calcium oxide? Can you write its formula? And therefore, a 1-to-1 ratio is CaO2, calcium peroxide. Now you'll notice that the formulas such as H2O2, Na2O2, K2O2, etc., they are not reduced to the lowest whole number ratio. Here's another exception to that rule. So don't write HO for peroxide. Don't write NaO for sodium peroxide. You see, all peroxides contain a pair of bonded oxygens, so they are left in that form. Well, congratulations. You've just completed Inorganic Chemical Nomenclature, Part 1 for binary compounds. Now there is also a second video dealing with the nomenclature of polyatomic compounds. And if you care to search for that, you'll find it on YouTube under the name Inorganic Chemical Nomenclature, Part 2, Polyatomic Compounds. I wish you well.